we have discussed hydrogen atom, and in the last class we have tried to see the radial equation and then try to find out the energy eigenvalues. And so let us try to summarize. So we found that energy eigenvalues. So energy eigenvalues are minus the value of Eg, which we wrote down, and then of course you have this epsilon n, and that is basically 1 by n square. Okay, so that is what I think you have. So if you look at this one, epsilon nl is equal to 1 by n square. So that is equal to minus ENL. ENL is epsilon NL into EG. Okay, so that is minus mu e to the power 4 by 2h bar square. So that is what we have seen. So that is equal to, of course, we call it as ENL, but we know that it is depending only on n. So it is minus mu e to the power 4 by 2h bar square into 1 by n square. Okay, and of course, remember in our notation, this E square is actually equal to QE square divided by 4 pi epsilon naught. We have used this as a shorthand notation, so we have to keep that in mind. And of course, QE is the charge of the electron. 1.6 into 10 to the minus 19 coulombs. So this is, and of course, we also have another important length scale of the problem, which we determined early on when we try to non-dimensionalize this differential equation. This is Eg that we have calculated, and h bar square by mu e square. That is the length scale. Okay, so we have A is equal to h bar square by mu e square. And this is what we call as Bohr radius. And so these are energy eigenvalues, and this is the length scale associated with that. Now, using fundamental constants, that is using electron charge and h bar and c. Okay, so these are fundamental constants. Okay, one can construct a dimensionless quantity. That is, you can write down E square by h bar c. So this is dimensionless. Okay, I mean, you know what E is in terms of the electron charge, as we have written it here, and this is what we call as alpha. Okay, and this is known as fine structure constant. Fine structure constant. And the value of this alpha, okay, so the value of this alpha is equal to 1 by 137. Okay, so this number is probably the much worshipped number in quantum mechanics. In fact, people like Pauli had almost worshipped this number because this occurs in every. So this is a very important number that you actually can make a dimensionless number. This is 1 by 137. So it is customary to represent everything in terms of this alpha. For example, if I want to write down Bohr radius, so Bohr radius, I can write down E square as alpha h bar c. Okay, so that is written as okay, h bar square divided by mu into, I write alpha h bar c. So this h bar will cancel with this. This is equal to h bar divided by uh, mu into alpha c. Okay. Now you can see that this alpha is a dimensionless number. So alpha c is a velocity, and m into that velocity is like momentum, and h by p is like wavelength. So this Bohr radius is that of a length dimension, as we know. And similarly, we can write down our energy. Okay, so let us recast energy. So energy is equal to En is equal to minus mu. So you can see mu by 2h bar square. Okay, let me put this 1 by n square here, and mu by 2h bar square into e to the power 4, which I will write it as alpha square h bar square c square. Okay, so this is equal to En is equal to minus 1 by n square into this h bar square, and this h bar square will cancel. So you have half mu alpha p the square. Okay, so again it is like half mass times velocity square is the energy, and then this is the energy written in terms of the fine structure constant. So you can see that uh, so that means the velocity of an electron in hydrogen atom is roughly of the order of alpha times c. So that is equal to, that means that is of the order of c divided by 137. Okay, which is kind of 1% of c. Okay, so which is, you can say, is much less than 1, and therefore using non-relativistic quantum mechanics, using non-relativistic quantum mechanics is justified. Okay. However, um, relativistic corrections to the energies, to En, are important. and are usually and are small, and therefore can be perturbatively calculated. Okay, so this is what we do in perturbation theory if we want to get calculated. So we want to get relativistic corrections, then we calculate them by using perturbation theory. And now, of course, the corrections are of the order of the fine structure constant. That means if you include relativistic correction, then there will be a change in the energy value in the second decimal place, because 1 by 137 is 0.01. So I'm just saying 1 by 137 is 1 by 100, so it is like 0.01. So your corrections will come in the second decimal place. So if for those phenomena where the energies are required up to 2 decimal place accuracy, then the relativistic effects are important. But if your accuracy is up to first decimal place, then ignoring these relativistic effects makes uh, no change to the energies. So that is so this alpha is some sense gives us an indication where the corrections will come up if you include relativistic corrections. So we will try to look at some relativistic corrections when we do perturbation theory. But this remark I wanted to make at this level so that we can expect what kind of corrections we would make. Now I want to, so also let me say that this is a problem which we have exactly solved. That means these energy levels we have obtained exactly. Now, uh, when we get some exact expression, okay, so we would like to understand in what all situations this can be used. That means what is the maximum physics that you can extract from this analytical formulae that we obtained, because not many cases we will be able to exactly solve. So uh, in getting these expressions, okay, so we have this mu, okay, and you can see that this mu is a reduced mass. Okay, so in getting these expressions, we have the following assumptions. Okay, so in getting uh, the expressions, expression for En, we assumed that the proton is infinitely heavy and is not affected by the motion of electron. So how do we know that we made this assumption? Because when we reduced two body problem to one body problem, and we said that the proton is considered as a force center, this is the proton, and that R you have an electron, okay, and then this is considered as a force center, and that is at rest. That means it is infinitely heavier. And instead of taking mass, we have taken mu, but this mu is more or less electron mass. This is also another uh, indication that we have chosen this to be infinitely heavy. Okay, so but this is, this is an assumption, and this assumption need not be true. Okay, so suppose if you have this mass of this force center, or whatever we considered as a force center, is not infinite, that is finite. So you know that um, so we can think of a situation where the masses are m1 and m2. Okay, so you have that is mass of the proton, mass of the proton is finite. So if I have to put in, then what happens? Then I cannot use mu is equal to me, but then in that case I use mu is equal to me mp divided by me plus mp. So in this approximation, I have used mu is equal to me. Okay. So now you can see that if you use for hydrogen atom, if you do this calculation with me, mp, me plus mp, you really don't see. I mean, what is the so you calculate your energy levels with the mu is equal to me, and calculate energy levels with mu is equal to me, mp by me plus mp. So you can write down this mu is equal to me into so I pull out an me, so 1 plus 1 plus me 1 by mp plus 1 by me. Okay, mp by, is that correct what I'm making here? So we know that 1 by mu is equal to 1 by me plus 1 by m, correct? So that is equal to 1 by me. If I pull out, then this is 1 by uh, so me by m, correct? So 1 by mu is equal to 1 by me if I pull out. So then if I take this, this will be 1 by me plus 1. But this one, me by mp, me by mp is roughly of the order of 1 over 2000. That means the value is going to change. So if this is 1 by me, this is instead of 1, it will be 1.0001. Okay, so it is going to change very, very limited. So there won't be any change in your energy levels, because their change is only in third decimal place. So this is much smaller change than even the relativistic effects. So it is fine. So one can use, so using mu is equal to me is fine for hydrogen atom. That means the infinite mass approximation, that proton has infinitely heavy, that seems to be fine for hydrogen atom, considering the considering the large difference between the mass of the electron and mass of the proton. Okay, so this is a good approximation. So this is fine to calculate this one. Okay, so but we have something called uh, other isotopes of this hydrogen. For example, you have deuterium, tritium. Okay, so deuteron and triton are the isotopes, but you can like hydrogen atom, you have deuterium. Okay, so deuterium. Okay, so deuterium is just like hydrogen atom. So you have you can call this as maybe D atom. So what is deuterium? Deuterium is it has its mass is higher because there is one proton and one neutron. Correct. So you have so you have a nucleus, and in the nucleus you have a proton and a neutron, and then there is an electron. So what is the change between this and that? Your reduced mass will change. That means your reduced mass now will be equal to um, kind of now you can say that this 1 by mu is equal to 1 by me. You can assume that proton and neutron have got same mass. So the mass of the nucleus is 1 plus me by 2 times mp. Okay, so that is 1 by me plus 1 by m. So now what happens? This is even heavier than the previous one, right? So what happens? Your mu will decrease, isn't it? Because this is 1 point. So me by 2 times mp is smaller than me by mp, correct? So me by 2 times mp is smaller than that. So this will be smaller. So let us say I call this as mu d. Okay, so 1 by mu d, 1 by mu d is this is 1 by me, 1 plus this will be a smaller number. So this is smaller than 1 by mu h. Is that correct? 1 by md is smaller than 1 by mu h. So which implies your mu d is larger than mu h. Um, yes. So mu d.
Sir, in the last case, ME by MP is only 1 by 2000. MP by ME is 2000, right? No, sir?
mp by me is 2000. Yes.
So, but you have given here mu is equal to ME is 1 plus this number. So, this is a higher number, so this reduced mass. Because mu is equal to ME is 1 plus this because here you are taking 1 by mu, but here you are taking 2. If you consider mu, it will be a higher number.
So yeah, that's what I was wondering. So suppose if I take mu is equal to me into mp by me plus mp. So that is equal to me into, let's say, 2000 times me divided by me plus 2000 times me. So that is equal to me square into 2000 divided by ME into 2001. So this will cancel, so you get this to be equal to ME. So if this number is large, then this will be same as ME. So now I want to ask, so mu by ME, right? So mu by ME is equal to MP divided by ME plus MP. Okay, so that is basically, it is like this can be neglected. You have mu is equal to that is equal to MP divided by MP into 1 plus ME by MP. So I think I knocked this off. So this is ME by MP is small, so I can write this as 1 plus ME by MP to the power minus 1. So that's what I want to write. So this mu by M, our mu is equal to ME into 1 minus ME by MP. I will keep the first term in this binomial expansion. So mu is roughly equal to this. But this itself is very small, and hence, okay, I think this is the correct expression.
Yes, sir.
Yeah, so if this is the correct expression, then what we will have is for mu hydrogen, I have Me into 1 minus Me by MP, correct? And for mu deuterium, I have Me into, okay, this is also approximate, but because I have neglected all the higher order terms, so 1 minus Me by 2 MP. Okay, so assuming this is okay, assuming a mass of proton and neutron are same. Okay, and then if you take mu of tritium, that is equal to Me into 1 minus Me by 3 MP. So in each of this case, so Me by MP is a larger number compared to these two. So that means we have this order. So mu H is, so a smaller number is subtracted from N and multiplied. That means we have 1 minus this is large and 1 minus this is small. So I think we have this order, right? Mu H is greater than mu D is greater than mu T. I mean, less than, right? Because this is going to be smaller and smaller and smaller, because um, 1 minus Me by 3 MP, 3 times MP is greater than 1 minus Me by 2 times MP, greater than 1 minus Me by M. Correct? So I think that is the conclusion that we have drawn here. So yeah. So this seems to be the situation. But how observable this is, of course, is a question. But then one can understand this to be like this. Now, if you go back to your energy level, Okay, so the only expression where this change will come is this mu. Okay, now this mu is increasing. That means the numerical value will decrease. That means actual energy will decrease because of this negative sign. Okay, so now what is the conclusion of this? Conclusion of this is that uh, if you actually look at the optical spectrograph of these atoms, okay, so if you look at optical spectrograph, and these experiments have been done. So in optical spectrograph, what you see is that suppose you take any particular spectral line, okay, so the wavelength of a spectral line, so let's say let lambda, um, so let's say lambda I, so we call this as wavelength of a spectral line um, of a particular spectral line, maybe some first line in the Balmer series or something. So particular spectral line, say some first line in Balmer series. Just say one of those lines. And here, of course, this index I will be hydrogen atom, deuterium, tritium, like that. Then we have the following situation. The wavelength for the tritium will be longer than the wavelength from the deuterium is longer than the wavelength for the hydrogen. Okay, because as I told you, since the reduced masses are different and the energies will decrease, that is bound state energies will decrease, and energy difference also will decrease, and energy difference will tell you the frequency. So frequency decreases, that means the wavelengths will increase. So this is what you call as nuclear mass effect. So this effect uh, is experimentally uh, observed for this for using this optical spectrograph of this. Now there is another system which is slightly better in terms of observing this one, but though it is very difficult to do an experiment of optical spectrograph, and that system is called something called muonium. Okay, so muonium is something like this. Just like electron, you have something called muon. Okay, so muon, and muon actually comes like electron. So you have something called mu plus, and it has an antiparticle mu minus. So mu plus and mu minus. Now the mass of this muon is something like 207 times that of the mass of the electron. So it's actually a heavy electron. Okay, charge is same as that of the electron. Now, if suppose I think of having a mu plus at the center instead of a proton, and then have an electron. Okay, so then this is like a hydrogen atom, where instead of a proton at the center, then you have a mu plus, and that is what is called muonium. Now, what is the advantage of this? Advantage is that so you can see that the mass of the proton is 2000 times that of the mass of the electron, whereas this is only 200 times. That means you will have some 10 times more effect you can actually observe in this. So that is what. So that means if so, I'm sorry. This mu is for mu1, and then this reduced mass also we have talked about mu. So maybe I should now write it as mu1 or muonium. Okay, so muonium will be equal to mass of the electron times 1 minus mass of the electron divided by mass of the mu particle. So instead of 1 by 2000, it will be 1 by 100. That means here the change is in the second decimal place. And if you look at, if you calculate this optical spectrograph, then you will see that this one is very much close between lambda h and uh, so you, you will see that this is um, much closer to hydrogen. That means it will come somewhere here. Okay, so this is what I would expect if you consider lambda mu, but this experiment is not done, so it is not
because
giving
of the
experiment.
because of the lifetime of muon. I guess lifetime of muon is very less.
Yeah,
It's
yeah,
2.19 microseconds.
yeah. So I think muon lifetime is very small, so it decays very
Very
fast.
fast.
Yeah, so about 2.2 microseconds, I guess.
2.19 sir, exactly. Sir.
So that is, it decays very fast, but the formation of this muonium is something which one can experimentally verify. That is, muonium exists. That is something which one can experimentally verify, because this muon actually decays into positron and some two neutrinos. So when muon decays into positron, so like for example, muonium forms. So this is something that we can experimentally verify, because when mu plus uh, decays to a positron and plus some two neutrinos, okay, I'm not worried at this moment flavors of these neutrinos. Let's just call two neutrinos. So now um, these positrons are emitted in the direction of the spin of the muon. Okay, and this directional dependence is a very famous parity violation in the weak interaction, because muons decay through weak interactions, and weak interactions violate parity. So if you have some spin direction for this muon, and positrons will be emitted in that direction. So that is some. So by noting down the direction of the emission of positron, you can fix the spin of the muon. Now what happens if the muonium has formed? Then there is a coupling of the spin of the spin of the muon to spin of the electron. Okay, if it is a free muon, there is no coupling. All the positrons that come out of this mu plus dk will be along the same directions, and from that direction you can find out what is the spin of this muon. But if muonium has formed, then the electron spin and muon spin will be coupled. Now if they are coupled, then what happens is, if you apply magnetic field, then the spin of the muon will actually precess around the spin of the electron. That means the spin direction will actually be changing with certain precision frequency. So your positrons that are emitted, that direction also will change, and there is some kind of a frequency with which it changes. Okay, so this frequency one can calculate theoretically, and then you can observe the muon decay in the presence of magnetic field. And from, so if there is no bound state formation, then this precision will not be there. By observing such a precision being there in the experiment, you can confirm that the muons, the mu plus that is decaying is a part of muonium. Okay, so that is one thing which tells us that this muonium can form. Now there is also another interesting system. It's called positronium. Okay, so this is basically like a hydrogen atom again, where instead of a proton, you have a positron. So you have a positron at the center, and then the electron. So electron-positron bound pair. Okay. So this is called positronium. So in this case, you will see that this mu is equal to half of the electron mass. Mu is equal to half of the electron mass, because mass of the electron and mass of the positron are same. So if you look at the Bohr radius, for example, so Bohr radius is given by h bar square by mu e square, right? So, or you can write this as uh, h bar divided by mu alpha c. Okay. So now you can see if mu is m by 2. Okay. So a positronium is equal to 2 times that of the a hydrogen atom. 2 times that. So positronium's Bohr radius will be twice that of the hydrogen atom. And what happens to the energy levels? So energy levels are given by minus half mu alpha c the square into 1 by n square. Okay. So now if mu is equal to me, and this is me by 2, so you will have energy levels for positronium is equal to half of the energy levels of hydrogen atom by 2. So this kind of so these what I'm trying to say is that most of these systems we can get get the energy levels and this kind of information by just the expressions that we have actually calculated. Now there is also an interesting and very surprising cases where we can use this. So I want to just try to share this, and this is also related to some other context which probably you are studying. So I'm going to look at an example of a completely different situation. Okay, so let me say that. Okay, so before that, let me also talk about something called hydrogen-like atoms. Hydrogen-like atoms. Okay, so many things come under this category. Just to give you an example, for example, if you have sodium atom, okay, sodium atom has got, of course, I'm now trying to bank on some knowledge which you already have on this electronic configuration. So sodium atom has an atomic number of 11. So that implies its core shell up to p core shell is filled. Okay, so I'm just trying to write it, assuming that sometime you have seen this, even though all this we have to understand only from hydrogen atom and something more than hydrogen atom that we will do later. So 1s to 2s to 2p6 3s1, even though this is taught in school nowadays. So let's assume this. That means the only this electron is kind of what we call that as a valence electron. That means it is free to participate in bonding and things like that, are free for donation and things like that. So that means now let's say that you have a 11, that is you have protons and neutrons. So let's call this as nucleus, and then there is some kind of a electrons, some 10 electrons. And as far as these 10 electrons are concerned, they don't really participate in the mass. So there is only one electron here. So now if you consider this entire core electron plus nucleus as some kind of an effective nucleus, then it has simply charge plus E, right? But its mass is different. Okay, so its mass is different. So you can see that uh, so if you are trying to look at this as a hydrogen-like atom, then wherever E is there, okay, so nuclear charge is Z times E. So the potential will be minus ZE square divided by R. So you can see that wherever E is there, so replace E square by ZE square in hydrogen atom. So wherever E is occurring, you replace E by ZE square. So in that case, what happens is your energy levels. Okay, so your energy levels will involve. So you know that your energy levels En is equal to minus mu Z square e to the power 4 divided by 2h bar square into n square. So we have, this is the energy levels for this expression. Now this is equal to, you have minus half mu Z square into alpha c the square. So we can write it like this. Or this can be written as minus half mu into Z times alpha c the square. Okay, so this gives us typically in an atom of atomic number Z, the velocity of an electron is of the order of Z times alpha c. Now alpha may be 1 by 137, but as Z is increasing, then the relativistic effects become very important. Okay, so for high Z atoms, so this implies for high Z atoms, relativistic effects are very important, because whatever decrease that you are getting because of alpha 1 by 137, then you multiply. For example, let's say uranium Z is 92. This 92 by 137 is of the order of 1. So it will be important. Okay. In fact, you will be surprised that if you want to understand some system like gold, you have to do relativistic quantum mechanics. Okay, so if you want to understand why gold is of that color, why gold behaves in this way, and if you remember, gold has an atomic number of 79, and Mercury, which is just an adjacent element to gold, has an atomic number of 80. If you look at physical properties of Mercury and gold, they are poles apart. Mercury is a liquid and gold is a solid, it is a metal. So the properties just with one atomic number difference are so very different. So it is always, you have to understand that one only from some of them you can understand from quantum mechanics, some of them you have to understand from relativistic quantum mechanics, and some of them, I mean, all of them you can understand only when you do what is called quantum electrodynamics. So quantum electrodynamics is a final theory that will explain everything in a periodic table. Okay, so this is one aspect where you can talk about hydrogen-like atoms. So I am only trying to use these hydrogen atom results without actually solving these problems. These problems need not be solved because we can use these results. Now I am going to look at a problem which is completely different, and it doesn't appear to be related to this at all. But surprisingly, these results are going to be of some use there. So this is what I'm going to start with a problem in classical electrostatics. Okay, so let us look at a problem in an electrostatics. So this problem is something like this. So I have, so let's say I have an infinite conducting surface. So let me define the surface to be z equal to 0. So this is an xy plane. Z equal to 0 means it is an xy plane. Okay, so this is a conducting plane. It's a conducting plane, and uh, and it is grounded. That means I am making sure that the potential on this plane is 0. Conducting plane and grounded. Grounded. So now what happens? The grounded means what? The electrostatic potential, do not know what you call it. So let's say V is equal to 0 on the plane. Okay, it's an infinite plane. The full xy plane is, okay, it's an infinite conducting plane that is grounded. Okay, so now what happens at some point here? Okay, so let us say this is at some distance from this, which I will call it as some z. I put a unit, I put a positive point charge. Okay, so this is a point charge. And now I want to ask a question that what is the, of course, in electrostatics, you would solve a problem of what will be a potential in the region z greater than or equal to 0. What is the potential in this region? So these are some questions that you solve in electrostatics. Now, this problem is a little bit difficult to solve because physically what happens is uh, because of the field, okay, so Q produces electric field.
So I think method of images.
Yeah, so Q produces electric field, and then the conductor or the conducting plane responds to the field by uh, redistributing free charges on the plane. So what is the result? That means what? A surface charge, the surface charge density rho of x comma y, sorry, usually we write it as sigma comma x, sigma of x comma y, because it is surface charge is induced on the plane. Okay, this much we can say qualitatively, but unfortunately, but we do not know. We do not know sigma of xy. That is the reason why we cannot solve this problem as such. But what we do is we try to intelligently use another problem where this is what we call as an image problem. So we set up an image problem. Okay, so in the image problem, what we have, let's say this is your origin, and at z I have a plus q, and at minus z I have a minus q. I don't have a plane anywhere here. Now you notice that suppose if your aim is to, let's say somebody asks you solve v of x comma y comma z for z greater than or equal to 0. That means you are interested in this region. Okay, so as far as z greater than or equal to 0 is concerned, there is only one source, that is plus q. Minus q I have put in a region that is not of my interest. And if you write down the potential for this, at z equal to 0, it will be 0. That means at the boundary, v equal to 0 for this problem and for this problem. And we have a very interesting theorem called Uniqueness Theorem, which tells you that if you want to solve a Poisson equation for the potential, if the source and the boundary conditions are same, the potential is unique. That means the potential of this problem will be same as the potential of this problem. Okay, so this is what is the method called method of images. So we solve an image problem which is easily solvable, and the potential of image problem will be same as the potential of this real problem or actual problem, because the potential is unique given the source and boundary conditions are same in the region of interest. So now if you have this image problem, many of the things of the image problem will be valid for this. Okay, I'm not going to do this problem of solving the potential and all that now. But once you solve the potential, of course, you can also find out the induced charge. And that is, of course, the business in electrostatics. But now I'm going to do something which is very different. So I know that so now you can ask a question either in the actual problem or in the image problem, the force experienced by this plus q will be same. Now you ask, what is the force experienced? Okay, so force on q. Force on q is given by same electrostatic force. So F is equal to, you can say that this is minus, okay, it will be attractive force. So minus q square divided by 4 pi epsilon naught into 2 times z the whole square, because the distance is 2 times z. So 2 times z the whole square. Okay, so um, now I can write it in the following fashion. This I can write it also as a potential, because this can be written as um, minus. So I'm going to write this. Now let us say that this is an electron. Okay, so let us call this as an electron. Then this will be an electron charge, correct? So, but in this particular case, let me say QE square. Okay, and let's call this Q as an electron. Doesn't matter whatever charge it is, but electron also will experience the same thing. If it is minus here, it will be plus there. So this expression will not change. So this is equal to, I can write this as minus QE by 2 the whole square divided by 4 pi epsilon naught into z square. Okay. whatever 2 that is there in the denominator, I just sent it to the numerator. So I will write this as QE by 2. Okay. Now I can write this. Suppose if I write F is equal to minus dV by dz. Okay, some potential is there. Then I can immediately write down this V of z. V of z is equal to minus. Now let me write it as E by 2 the whole square. E by 2 the whole square divided by 4 pi epsilon naught into z. Sorry, there is no 4 pi epsilon naught. E by 2 whole square by z. Now you look at hydrogen atom. So compare with the hydrogen atom. Hydrogen atom, what is the potential? V is equal to minus E square by R. Now R is like Z is like R, and E has to be replaced by E by 2. Now suppose if I ask a question that so the question that we are asking is something like this. Suppose I have this metal. Okay, I have this metal, and then let's say there is an electron here which is having this kind of a potential. Okay, now is it possible that there are some bound states? That means there are some electron bound states here such that this electron can stay in these bound states. Okay, so what I'm trying to do is, just like positronium, I'm going to talk about a bound state of image charge and the real charge. If such a bound state exists, what are the kind of energies that these electron levels will have? So I'm going to use this hydrogen atom result. So I don't have to do much. All that I have to do is, for this problem, the energy levels are going to be equal to, of course, bound charge and this charge will have same mass. So this is equal to minus 1 by n square into, so I have mu is nothing but mass of the electron divided by 2, me by 2, me by 2, and then you have mu e to the power 4. E to the power 4 is e by 2 to the power 4 by 2 h bar square. Okay, me square, mu is square divided by 2 h bar square. So this is going to be your energy levels. That means if you look at this, this is minus 1 by n square into, if you calculate me to the me into e to the power 4 by 2 h bar square, this is the hydrogen atom energy levels. Okay, and what are the other things that I have? I have 1 by 32. Correct. That means whatever is your energy level, for example, ground state energy, if you want to get ground state energy, so ground state energy E1 is equal to minus 13.6 electron volt divided by something like 32. Okay, so this is some very small energy in electron volts, and then one can now ask a question. So I am getting these energy levels. Now, is there some experiment which you can do to verify whether my calculation is correct or not? And it turns out, I think maybe some 20 years back, there was some experiment done by using photoelectron, what is called photoelectron emission spectroscopy. So they try to send some photon and try to ionize the electron in one of these bound states, and that electron will be so its energy will be measured by scattering another photon from that electron. So using this kind of an experiment, people found that this kind of energy levels are indeed true. There are some bound states, and these bound states occur, and So of course there are some differences. It turns out that people did not see it is exactly 1 by n square, but there is something called some quantum defect they call it. So 1 by n plus a the whole square, but a is same for all n, and hence it is easy to fit that parameter and get the value of a. Okay, so now why is this very important is because nowadays when you have this so surface states of materials is very important, because for example in chemistry and biology there's something called catalysis. So catalysis is one process where the surface states play a very important role. Actually no chemical reaction takes place, but there is some kind of a surface states that are involved in enhancing the reaction and things like that. So in the field of catalysis these surface states are important. And also there are other nanoscience etc where the surface energy is much more than the surface is more than the volume. The surface states seems to play a very important role. So there is a lot of current relevance to these things, but what all we are doing is we are actually taking the same old energy eigenvalues which we know from 1913 when Bohr first calculated, and from there we are actually trying to reinterpret them in terms of the new situation. So sometimes it's very important to understand how what we learned. Maybe this is hydrogen atom is just like alphabets of quantum mechanics. So using alphabets, sometimes if you can uh, write a write a nice poetry, then it is very interesting. So this is, I like this problem very much because this is something which very reasonable um application of the most fundamental results that we have in hydrogen atom. Okay, so these are some of the important problems that we might actually uh, do when we look at this hydrogen results. Now I want to look at a slightly different problem. So this is with respect to this surface states of on the metal surface. Okay, so that is what we have. Now let's try to ask a question that suppose if we put this so now let's say that let's put this hydrogen atom in magnetic field. Okay, so basically a uniform magnetic field. Hydrogen atom is in a magnetic field. Usually we talk of some perturbation theory if we have to solve this problem, but we will see if we can do something without this perturbation theory. Now, for that, let me just so we have the so let me just use a particular language to describe this. So we talked about so let's say we have solved for hydrogen atom H psi NLM r theta phi is equal to En psi NLM r theta phi. Okay, so your psi NLM, we did not of course talk about psi NLM completely. R theta phi will be equal to some normalization constant which depend probably on N, L, and then there is some radial function NL of R into YLM of theta phi. So this is our wave function for this. Okay, so of course radial functions we did not see yet, but I don't want to work with this, so I'm going to use Dirac notation. Okay, so use Dirac notation. So I'm going to represent uh, stationary states. So in Dirac notation, what I will do is I have these quantum numbers n, l, m, and that is my state. That is equal to En into n, l, m. So it is customary to represent the state in Dirac notation involving quantum numbers associated with the complete set of compatible observables. So in this case, we have n corresponding to Hamiltonian, L corresponding to L square, and M corresponding to LZ. So the quantum numbers associated with three completely commuting set of compatible observables, we have NLM. So in the Dirac notation, this is what we represent. Okay, so what is so H acting on this is this. I already wrote. Now L square acting on this NLM is equal to H bar square L into L plus 1 into NLM, and LZ acting on NLM is equal to H bar M NLM. So that is how these states are there. Now we want to ask what happens, and as you know that the Hamiltonian, so in the presence of magnetic field, so in the presence of uniform magnetic field, let's call that as some B, vector B. You know from electrodynamics that this B can be obtained from a vector potential. So B can always be written as A, curl A. Now if you have a uniform magnetic field, okay, so this is something which you can show, or probably you have already shown it. This is equal to half B cross R. So this you can show that this vector potential will be giving you a uniform magnetic field. And the Hamiltonian is something which you do this from your Lagrangian in classical mechanics time. So the Hamiltonian is obtained by replacing the momentum vector by P minus QE into A, where QE is the velocity of the electron. So the Hamiltonian is given by P minus QE. This is the charge of the electron into A, the whole square, divided by twice ME. Okay, I'm assuming that this proton is infinitely heavy and all that, plus of course your V of R. And your V of R is where V of R is minus QE square divided by 4 pi epsilon naught R. Okay, so Now remember that this P and A are operators because P involves X and so on. So one has to be careful in expanding this. So this is equal to P square by twice ME plus V of R. So let me write this together. Then I have a linear term in A. Okay, so that is given by minus QE divided by twice ME, okay, into P dot A plus A dot P. I cannot write them as 2 times P dot A because A involves position operator and P involves momentum operator, and we know position and momentum don't commute, so one has to be careful and write it this way, plus QE square divided by twice ME into A square. Okay, so we can write this Hamiltonian as some kind of H0 plus H1 plus H2. Okay, so I'm going to call this one as H0 and this term as H1 and this term as, that is basically if you put A is equal to 0, I mean B is equal to 0, then you will get only H0. Correct? So now let us look at H1. This is basically our hydrogen atom. So this is hydrogen atom without magnetic field. Now let's say we have this H1 and H2 terms if you apply magnetic field. And now let's look at the second term. So H1 is equal to minus QE by twice ME into, so A is, there's another factor 2, so that comes to be 4, and P dot B cross R plus I mean B cross R dot P. Okay, so yeah, now notice that B is a vector. Okay, so notice that B is a vector. I think I am a little bit sloppy in not writing these operator signs. R is an operator, P is an operator, but B is not an operator. B is a vector, but not an operator. So therefore, you can actually commute this B. So this is a triple product. Okay, so and you can cyclically. Okay, so you know that P dot P dot B cross R can be written as P cross R dot B. Okay, so one can write it like this. Also, you can write down B cross R dot P, which is same as P dot B cross R. Oh, it's not the same. So dot P is equal to P dot R cross. Okay, so is that fine? So now what you can see is yeah. So now it is like you know that R cross P, R cross
So,
P is L.
so first form, I think it is wrong. P dot B cross R. It should be P dot P cross R, right? Why P cross R? That is what vector algebra tells. You cannot dot product it post. I always saying it is P dot.
Actually,
P dot.
this is a triple product. Any order you can write, but only thing is you should not interchange P and R. Okay, that's all that you have. B dot P cross R is same as P cross R dot B, right? See, you know, when you have some three vectors, A dot B cross C,
It's
A
B
dot B
dot.
dot A cross C is same as C dot A cross B, right?
Yes.
So that way, this is cyclic basically.
That I understood, sir. But pre dotting it and post dotting it, that is what you have confused. You can do it after also. So it doesn't make change.
It can be written as R dot P cross B or B dot P cross R. So you might want me to write this as B dot P cross R.
Yes, that's what I'm
But
doing.
dot product
Make
anyway commute, so it doesn't matter.
commutes.
So maybe if you want, I can write it like that. So B dot. So R cross P is the angular momentum operator. But now you can see that uh, okay, I think I have to be careful because this is an operator. So I have to write. So let me see. So I have this can be written as B dot L. Okay, and this I have to write it as minus L dot B. But this is an operator. So if you take a state and then operate B dot L, and then in other case you operate L dot dot B L. So this can be written as B dot L on alpha plus L dot B, B dot L on alpha and L dot B on alpha. So minus will be equal to these two things. So this will be equal to, so these two things together. So B dot L alpha will cancel.
So one thing is for the first term P dot B cross R. So can we write it as B dot P cross because it is anti-cyclic, it is the inverse of the cyclic is making it.
So what I'm trying to say is that P, okay, let me put it this way. So is that first correct? So I write P dot B cross R and B cross R dot P. Okay. So now I can write So P dot B cross R can be written as R dot P cross B, right? Or that can be written as B dot R cross P, correct?
Yes.
Okay, so this is fine. Now the next one is I have B cross R dot P, which is okay, B cross R dot P, which I can write it as P cross B dot R that can be written as R cross P dot B.
So, but as long as the cycle is remaining the same, we can interchange this dot and cross, and so it will become the same term, right?
Okay. So if it is becoming same term, then there is no problem. So I will have R cross P, L dot D term will be there, correct? So it is more convenient for me if it is becoming same term. That is equal to H1 is equal to minus
So I think the confusion was that the first term that you B dot B cross R, that is, I think it will come minus sign.
okay, so this is cyclically this is fine, right? So that is equal to, I will get two terms. So minus QE by twice ME into that 4 will become 2 because I will get two terms from here, and that is L dot B. L dot. So this is the Hamiltonian that I have for H1. Now let us look at this one. Now let us say that, so let us say that let us choose our B to be some kind of a B0 in the Z direction, in the K cap direction. So the applied field is along Z direction. So if you do that, then your H1 is basically minus QE into B naught divided by 2ME into LZ. And this is the only operator that we have. Okay. So you can now write down. So you can ask a question, what happens to if I keep this H0 plus H1 and then operate it on NLM? What happens is H0 operating on NLM plus or minus QE B0 by twice ME, LZ operating on NLM. Now you can see this is H0 on NLM is basically En minus QE B0 divided by twice ME into, this is MH cross. Okay, so this is the new energy, NLM. Okay, so normally we define something like this, QE H cross divided by twice ME. You define this as some mu B. This is called Bohr magneton. This is kind of a fundamental magnetic moment. Okay, so then you have H0 plus H1 acting on NLM will give you En minus, okay, En minus mu B into B0 into M. So you can see that now this energy depends on N and L, sorry, N and M. Okay, so that means so the part of the degeneracy gets lifted. Okay, some degeneracy is lifted. That means different values of M have got different energies here, and because of this, your uh, your spectral lines will actually appear as if they are split, because now your energy levels are not degenerate, and hence your frequencies will be different from different energy levels. And this is what is observed in Zeeman effect. Of course, you require to because the value of mu b is very small, in order to have an appreciable shift in the frequency, you require to apply very high magnetic field. And Zeeman had done these experiments much before even Planck's discovery of quanta. I think in late 19th century, 19th century, Zeeman had discovered that this splitting of spectral levels has happened. In fact, I must tell you, it's a nice work by Lorentz. He used classical electrodynamics to actually explain the Zeeman effect, and he explained. The only thing he could not explain was an anomalous Zeeman effect, but normal Zeeman effect can be explained by using classical electrodynamics. Okay, so this is one. You don't require perturbation theory even directly, because the Hamiltonian with this interaction is having only LZ operator, and NLM is an eigenstate of LZ operator, and hence you can get exact energies where the degeneracy in M can be lifted. Now, if you look at the next term, but you can also see that this term is much smaller. Okay, so your mu b, as you have seen, mu b is equal to QE into H cross by twice ME. Okay, so this is very small. Compared to, of course, compared to uh, compared to these energies, compared to energies corresponding to En. Of course, I should not compare with En. That is mu b into b naught. So this is very small compared to En. Per uh, usual fields in the laboratory, and hence only for very high fields you observe this splitting takes place. Now the second term is much smaller than the first term itself, because you remember this A is like amplitude, the vector potential amplitude, and it is A square. So this is even weaker. Okay, so sometimes uh, there is something called weak field approximation. Okay, so H2 is neglected, and we call this as weak field approximation. Okay, it turns out that this H2 is much smaller than H1, and which is much smaller than H0. That is the order in which these things are there. So if you want to get something of H2, so we can get the effect of H2. Okay, so effect of H2 can be seen only if H1 is H1 is not present. Okay, sometimes H1, for example, if M is equal to 0, then that is 0. So if H1 is not present, then you can look at the effect of H2. Okay, so this is how we will proceed in addressing the problems in in the presence of fields and things like that. Okay, so maybe more in terms of these interactions and fields we will talk when we do perturbation theory. But right now I want to just leave with this illustration of how you use this. So I want you to notice that here I don't know I don't know the wave function, but I'm still able to manage a lot of information, because by just representing this in this Dirac notation, now I will be able to even get the effect of magnetic field change in energies, and all the frequencies can be calculated. So that is the advantage of abstract notation. Okay, so now let us go back to one of our expressions that we left in the last class, namely the recurrence relation. Okay, so we have talked about yeah. So okay, so we have this radial equation, etc., etc. So I think we have this differential equation, and we have these solutions. So what is important is that we have found out S is equal to L plus 1, and then we have this recurrence relation. Okay, so let us try to get this recurrence relation. So we will be interested in the radial wave function. So we will start with our recurrence relation like this. This is our recurrence relation. And then we had U of rho is equal to rho to the power L plus 1, which we have figured that out. And then J is equal to 0 to infinity Cj into rho to the power. So this is our, and then we had written a J max plus L plus 1 is equal to, we called it as N, right? So that is what we had called it.
So what is
Hello? So J max plus L plus 1 is equal to N. So this is what we called. Now we can, of course, you also, this is what we called as, sorry, this is basically not U, this is F of rho. So what is U of rho? U of rho is equal to, basically it is proportional to rho to the L plus 1 into F of rho. No, this is a part of that. So F of rho into e to the power minus rho. So that is what minus rho into some lambda k. Now, of course, we called it as lambda nf. Okay, so now what we will do is we'll try to fix some value of n. Suppose if I fix, suppose if I fix fix n is equal to 1, okay, so that means your, so the maximum value, so j max is equal to n minus l minus 1. So if I say n is equal to 1, that implies l is equal to 0, correct? So that means if I say this is 1, 1 minus 1 is 0, that is the maximum, that is the starting point, right? J max has to be positive, non-negative. So L is equal to 0. So that means I will get C0 is some value. So I will get 1. So we can go back and substitute it in this expression. Okay, so let us try to write that. So C1 is equal to 2 times lambda NL into, so J, so there is only one value, right? So that is J max, J equal to J max. Or J equal to 0, this is equal to 0, so this is 1, and minus 2 divided by 2 times 1, and that is 0. So 2 will cancel. So I have lambda NL minus 1 into C naught.
So we're fixing j equal to also 0.
Yeah, so J equal to 0, then only I will get C1 here. Correct. So n is equal to 0. There is only one term basically, that is a constant term. J equal to 0, L is equal to 0. Okay, so lambda KL is what? 1 by n, right?
Sir,
So
how?
that is also 1.
Excuse me, sir.
So C1 is 0.
Excuse me, sir.
Yeah.
So how this lambda KL is written as a lambda NL in the when you are writing recurrence relation again by putting L is equal to 0?
Yeah. See, K was general. So I have found this lambda KL to be equal to 1 by n, right? So since this is depending on n, I will call it as NL. That's all. When I don't know what it is, I call it as K. So this is equal to NL. So if I substitute all these things, so let us say I put J equal to 0, L equal to 0, and then this is equal to 1, then this will be 2 minus 2. That implies C1 is equal to 0. So what remains is just C0. So the wave function corresponding to, let's say, U10 of rho is equal to rho to the power L plus 1, right? So that is rho into C0, there is some C0 into J equal to just J equal to 1, 0 to C1 is anyway 0. So that means that is just C0 from this f of rho term, and then e to the minus rho. So this is the wave function. But then we know that what we R10 of rho is equal to U10 of rho divided by, so basically R10 of R is equal to U10 of R divided by R. Okay, so if you want to call it rho, then R is basically R by A, right? So this is our non-dimensionalization of R. So R is equal to rho into A. So this will be some A into rho you have to write. So this rho and this rho will cancel. So you have R10 of rho is equal to some C naught by A into e to the minus rho. Now, of course, you have to rho is equal to R by A, so you can substitute that. So let us say your R10 of R is equal to C naught by A into e to the minus R by A. But then this has to be normalized by uh, by normalization. I mean that you must take 0 to infinity R10 of R modulus square into R square dr. That should be equal to 1. So why R square dr? Because you have to normalize the entire wave function. Okay, so remember that normalization is not for a part of the wave function. So actually you have to normalize um, the wave function like this: R10 of R into y00 of theta phi, this mod square, and then you have integral over R square dr, and then sine theta d theta d phi. Now this part of the wave function, mod square of this and this is already equal to 1. And hence, if you want to normalize this part with R square dr, you have to retain here. And that is very important. Sometimes people don't remember this. So you will get wrong result if you do. So that means your C naught square or mod C naught square by A square into integral 0 to infinity dr into R square into e to the minus 2r by A naught, 2r by A. Okay, so this is equal to 1. So that means, this, so you write down 2r by A to be some psi, then dr is equal to A by 2 d psi. Okay.
So we can do integration differentiation sign. 5 minutes.
Yeah.
That is
So that is A by 2 d psi, and R is equal to A by, so C naught square by A square into A square by 4, and of course 1A by 2 integral 0 to infinity d psi square into e to the minus psi is equal to 1. But this is a gamma function, gamma 3, which is 2. So you have C naught mod square into A cube. A cube, of course, there is a square in the denominator, so that will give you A, and divided by 4. That is equal to 1. So C naught will be equal to 2 by square root of A. So this is what we have, this normalization. So then you have your radial function for R10 of R is equal to 2 divided by A to the power 3 by 2 into e to the minus R by A. So this is basically your radial wave function for the ground state. So n is equal to 0, or what you call as 1, 0, 0. This is the ground state. And this is the ground state wave function. Okay, so if you plot this ground state wave function, then it will be something like this as a function of R. So R10 of R. So it will be some value at R is equal to 0, and then it will decrease exponentially. Okay. So this will be your ground state wave function. But then you can also ask what is the probability density. Okay, so probability density of electron in the ground state. Okay, so that is if I denote it as P of R. So P of R is equal to R10 of R mod square. It's not that, it is R square into this. That is the probability. So because if you define probability density, then integral 0 to infinity P of R dr should be equal to 1. Okay, so that integral 0 to infinity P of R dr is equal to 1. And if R square is not included in P of R, it will not be equal to 1. So that is why this is the probability density. So that means your probability density is P of R is given by R square cos C naught by A to the power 3 by 2 into R square into e to the minus R by A. So this is your P of R. Now, if you want to plot this, you try to ask a question, what is dP by dr? dP by dr is C naught by A. Okay, I have not written. C naught is 2, right? So 2 by A to the power 3 by 2 into, I have 2R here, and minus R square by A, R square by A into e to the minus R by A. So if I equate this to 0, then I have R, so R into 2 minus R by A is equal to 0. R square, oh sorry, mod square, right? So that is 2R by A. So 2 by A here. 2R square by A, so 2R by A. So that implies R equal to 0 and R is equal to A. There is one, so this is either maximum or minimum, extremum. And if you actually plot, the probability density, so let's say P of R plotted in this way and R. So you can see that so let's say that this is your this is the graph of R10 of R mod square, and then you can have a graph of this is the graph of R square. Now when I multiply these two things, I will have something like this. And this maximum is what corresponds to maximum of where this is maximized. Okay, so that is the Bohr radius. So the maximum probability or the most probable value of R for the electron is the Bohr radius. Okay, but it's not that this is symmetric around Bohr radius, but because it will be there will be a long tail, it will go to 0 only at R goes to infinity. But this is the probability distribution of the ground state. Now I will leave it as an exercise which you can do is by using this recurrence relation, obtain normalized wave functions, normalized radial wave functions, for R 2 1 0. Okay, R2 1 of R2 0 of R. Okay, R2 1 of R and R2 0 of R. So obtain these two wave functions. Okay, and comment on nodes of radial wave function. Then also write psi 2 1 1 of R theta phi, psi 2 1 0 of R theta phi, and psi 2 1 minus 1 of R theta. So if you do this, then in the next class we will try to discuss a little bit about some linear combination of these solutions which are more relevant physically. Okay, so this entire thing in chemistry we call it as hybridization. So some hybridization is possible based on the symmetry involved in the system, and we can try to relate the symmetry group and then the hybridization of these molecular orbitals. So we will try to relate what we learned in group theory and this kind of molecular orbitals here, how hybridization takes place and things like that. Okay, so I will stop here. If you have a question, you can ask.
Excuse me, sir.
Yeah.
Sir, in order to find the probability, multiplying with R is a mathematical need or some theoretical need? I can't understand the reason behind it.
That is actually, it is basically the definition of probability density. So the probability density is, see, whatever is your, let's say, suppose your psi is some random variable. Okay, psi is a random variable. Then if you define some rho of psi as its probability distribution function, okay, then integral whatever some psi lower value to psi upper value, upper limit and lower limit, your rho of psi d psi has to be equal to 1. So here I cannot put anything different. So this has to be only d psi. Okay, so now the point here is that your R21 of R is just a radial function, or in general RNL of R is just a radial function. But RNL of R mod square cannot be probability, because we have, this is only a part of the so if, for example, if you take psi of R, okay, and mod square of psi of R, this is a probability density. And then when you take d3R and then integrate over the entire volume of interest, you will get 1. Correct? Now suppose if I take a piece of this wave function and then without taking the relevant integration measure, then I will not get separately that normalization. Correct? So this is, we are trying to relate the normalization of the radial wave function to the probability concept, and hence probability concept requires, if this were probability, then I must simply should have this to be equal to 1. But that is not true. So we cannot have that. So you have to keep this R square linked to this in defining your radial probability density, so that in that case, just by putting dr, it will be equal to 1. So it is this correspondence between the wave function. So the reason is, in quantum mechanics, you are using what is called square root of probabilities, which you never use in any other subject in physics. So this is a consequence of using square root of probabilities.
Okay, sir. And sir, because of this multiplication of R square, only we have this Bohr radius, right?
Correct. If you define probability density like that, then the Bohr radius turns out to be the maximum of the probability distribution.
And so one more question, sir. Like when we were talking about the hydrogen atom in the magnetic field, so we finally considered the degeneracy used to get lifted, right? But sir, I am confused here again because when we are adding one more energy, and then we are like when two energies coming, then why this degeneracy is getting lifted? Is it like degeneracy is getting cancelled or what? What does that mean, sir?
See, that means so basically whatever symmetry that was there earlier without applying magnetic field, that symmetry is now no longer there. The symmetry is broken. That means in the previous, when there is no magnetic field, there is some kind of isotropy, right? So direction doesn't matter. Whichever direction, all directions are equivalent. So you rotate in one direction, no change in Hamiltonian. But now there is a information of some direction, right? Applied magnetic field along z direction. So z direction is different from other directions. So that means that rotational invariance symmetry is broken. And when the symmetry is broken, then what happens is the transformation group now will be a smaller group, or maybe there is no group, no symmetry, in which case the degeneracy gets lifted.
Okay, so it's like magnetic field breaks the symmetry. That's why it is getting lifted.
Correct.
Okay. Thank you.
Sir, hello, sir.
Yeah.
Sir, probability doesn't depend on theta and phi, right?
So basically, in this case, I am asking what is the probability in R. Okay.
Yes, sir.
But you can also ask what is the probability in theta and what is probability in phi.
So for that, we have to calculate another radial probability.
No. See, the point is something like this. R, theta, and phi are three coordinates. They are independent coordinates. And therefore, you can talk about joint probability. That will be simply the probability distribution. You multiply one with the other. If P of R is the radial probability, some P of another Q of theta is theta probability, then you have to simply multiply them.
Yes, sir.
So you will have like if you take mod psi square of R theta phi, then you will get the probability density corresponding to R theta and phi, right? So that can be written as probability density of R multiplied by probability density of theta multiplied by probability density of phi. Probability density of phi anyway, it doesn't have phi dependence because phi dependence in the wave function is simply like e power im phi. So when you take mod square, that will cancel. So there is no that isotropy is always that azimuthal dependence is not there for the probability, but it will have dependence on theta and R.
Yes, sir. So theta and phi will depend on M and
yes, L and M.
Yes. Yes. Sir, and if we plot this graph, radial probability density, then as n increases, amplitude will decrease. Sir, why its amplitude keep decreasing?
Amplitude of what?
Amplitude of the radial wave function.
Why does it decrease?
Sir,
No, that
don't know, sir,
amplitude
what?
depends on your normalization constant, right?
Yes, sir.
So amplitude is what? It is related to some kind of a probability amplitude only, right? So as you go to higher and higher states for the hydrogen atom, the probability of electron being in the higher excited states will be less only, right?
Yes, sir.
So that has to reflect in the wave function.
Yes, sir. That's why it decreases. Thank you, sir.
Yeah.
Excuse me, sir.
Yeah.
So, like I have one more question which I forgot to ask previously.
Hmm.
So, like when we were like looking this image problem, so the first thing is like I always wonder like why this exists, like how this minus q charge is getting, like why this image charge is created. So if you could explain me that, that would be good. And I have another question, like can we solve it like whole image problem with a quantum mechanics? Like the whole why this is happening. And I have another question related to it. So like the energy level degeneracy exists, and because of that energy level, different energy level exists. So why can't same kind of energy level exist in such kind of image problems? So like what we had seen of the plate connected, grounded plate and charges present.
Why can't what is the last question?
Like sir, like why we can't have energy level in such problems, like where like image problem as we have discussed in our class today.
So yeah, so the point is something like this. First, let me just talk about your second question. That is, can we have complete quantum mechanical calculation to the image problem? That is very difficult because you have to consider in your model many electrons in the metal, and then see if you can put in actual potential, and it becomes a many body interacting system, right? So I hope that is what you had in mind. And such many body problems are
Yes,
not
sir.
tractable. So in fact, we will see that I will show you that helium atom cannot be solved exactly. Only hydrogen atom can be solved exactly. That is why we are trying to celebrate hydrogen atom, hydrogen atom, hydrogen atom. And once you cross hydrogen atom and go to helium atom, then you cannot solve exactly. You have to do some perturbation and variational principles and things like that. And so in the periodic table, the only one atom that you can solve is hydrogen atom. So that is why we are trying to use these hydrogen atom results in various other cases, or where these results are relevant to understand. So what maximum can we extract from this hydrogen atom results? That's what we tried today. I tried at least. So many body problem is not tractable. So that is kind of ruled out. Now the question is why that image charge? So there is nothing physical about that image charge. So it so happens that the point charge has got a spherically symmetric electric field, and since this has a spherically symmetric electric field, on a plane it will produce a circularly symmetric induced charge. Now the circularly symmetric induced charge can be mimicked by putting a negative charge there, because it is like in optics, if you have a point source and if there is a diverging beam, if the light is diverging, then you put a lens and then you can make it converge to a point on that on the other side of the lens, right? So if you have a focal point, the diverging light from here will actually get converged at that point. So this is also something like that. So this positive charge, these electric field lines are diverging from here, and this conducting plane is actually like converging these diverging rays into one point. So, and in electric field field lines, if you remember, these electric fields will diverge from a point charge, which is positive, and then converge to a point charge that is negative. So if I put a negative charge, physically we are having a situation like, now what happens if it is a conducting plane? All these electric field lines that are starting from positive charge will go and end there. So all these points will go perpendicularly end there. So that ending is something which we are mimicking by putting this. Of course, it is more easy to understand this mathematically. Mathematically, we are trying to create a situation. This problem is something which we cannot solve, so we are trying to solve another problem which can be solved, but it has same source and boundary condition in the region of interest, and hence uniqueness theorem assures that the potential is same for both the problems.
Okay, sir.
Yeah.
And so one more thing, like as you told that we solve a hydrogen atom and then we are using the result of it for another atom. So I just want to ask that we can do only when the relativistic effect is not coming to the picture, right? Like here for sodium, we wanted to put, so we just multiplied with Z square. So we have that freedom only till the point we don't have that relativistic thing coming into picture, right?
Correct.
Okay. Thank you.
Yeah.
Sir, I have a curious question. If, as we have done for hydrogen atom, if we can expand it to molecule and then classical object and try to compute with a giant quantum computer, can we get the classical equation of motion by solving the wave function? Just curious question.
So essentially, you are asking how do we correspond to a corresponding classical system? Suppose a hydrogen atom, by solving Schrodinger equation, can we obtain the behavior of, for example, Sun-Earth system or something like that, right? So which also has a similar.
Yes.
Yeah. So the point is that there is some correspondence to quantum system to classical system, but it's not very obvious. The correspondence is through something called Hamilton-Jacobi theory in classical mechanics. In fact, Schrodinger had gone exactly in the opposite way. So Schrodinger tried to get Schrodinger equation from Hamilton-Jacobi theory for optics. So Hamilton has developed Hamilton-Jacobi theory for optics. And since wave phenomena is like optics, so Schrodinger started from Hamilton-Jacobi theory for optics and then came to Schrodinger equation. So that is one direction in which one can make kind of a correspondence. But that is not done usually in textbooks, and it's not very seriously taken, because that is like a starting point of quantum mechanics, and that is also forgotten there. So the most spoken thing is that if you have quantum mechanics you do, and then look at average behavior of quantum systems, that means in terms of the expectation values, and you ask how these expectation values change with time, then the classical behavior will come out to the expectation values. This is what is called Untitled theorem. Okay, I do not know if you have heard of it. Otherwise, maybe I can show one day that there's something called Untitled theorem, which you might have done in your first introductory quantum mechanics course. Most likely it is done at that time. So Untitled theorem will tell you that average behavior, that is expectation values, evolve as according to classical equations of motion. And that is something that can be shown from Schrodinger equation.
Yes, sir. So, sir, classical object can have a wave function, but expectation value of them only behave like a classic.
We're not going to have a. See, there is also, the theory for macroscopic wave functions is also there, but that is not for one particle, but because any macroscopic system contains large number of particles, right? So it will be kind of a many body wave function for a macroscopic system. For example, that is what will take us to field theory. For example, you consider a superconductor. A superconductor has large number of electrons, and a superconducting sample you can see, right? In the laboratory, you do experiment and all that. So that sample will have a macroscopic wave function, and that wave function is something which is quantum mechanical, and there are many quantum features associated with that. So that is called macroscopic wave function, because that is corresponding to a macroscopic system.
Yes, sir.
So, but when you tell it is macroscopic system, in that case, position momentum can be what found out simultaneously. So there is no uncertainty there, right? When I tell this macroscopic system.
Yeah.
That is.
Yeah, the point is that whatever uncertainty that we are talking about is in comparison to H cross, right? So H cross, when it becomes very, very small, then uncertainty cannot be observed.
So then, yes, sir, I understood that. But then, how we can say that wave function is quantum mechanical features? When this uncertainty goes away, when we are not worried about this length system itself, when the system itself changes, we have to treat this whole system classically. Then how we can expect some quantum wave nature of that macroscopic system? You told now.
There are two things here. One is whether there exists a wave function or not. Second thing is whether you can observe wave phenomena or not. Wave function always exists because everything you do in classical mechanics you can do with quantum mechanics. But
yes, sir, that's
those wave phenomena may not be observable, and hence, but you can still do calculations. You can, for example, you want to understand a pendulum experiment in the laboratory. You can write down Schrodinger equation and then calculate everything that related to pendulum mathematically. But then, whether any of those quantum effects can you observe? You cannot observe because that system is, I mean, its system's action is so large compared to H cross, and hence you cannot observe it. But it exists. You can actually do calculations, though it is
yes,
difficult
sir, yes,
and unnecessary. But in principle, you can do those calculations.
that's right. Sir, when you did that calculation for this, yeah, go ahead, sir, go ahead.
So, like, I wanted to ask us what Arup Jyoti asked, like, can we solve this classical body problems without approximation? Like, if we are not, we are able to solve all these classical body problems without any using any approximation. So I think that's what we are doing quantum mechanics, right? Like, when we are not generalizing, we are not approximating anything. So if we are regularly solving, is that's what more like quantum, you know?
Yeah. That's true.
Sir, when you did that, calculate that for conducting plane, that part, for that electrostatic energy will be half, sir, for the original system and the image system. I think the energy will be half of the system which we consider, isn't it, sir?
Electrostatic energy. Electrostatic energy is always defined as in some region, right? So
No, sir, I'm asking the energy difference between those two systems, the image system and the original system. The energy should be half of the original system. That's what I'm saying.
energy is, so basically when I calculate this potential, it is the potential experienced by the charge under consideration.
Yes.
So that is the point charge that I have kept outside. I have no control on the image charge. That is, I mean, it is not there actually in the actual problem. I have only a metal. Image charge is like our image in the mirror.
Yes, sir.
There only when you see it in the mirror.
But I read, I think in Griffiths he has mentioned that some quantity will be half from this original system. Which one is that, sir? If I'm true that one quantity when we calculated, it turns out to be half of the mirror system in this original system. But which quantity is that, sir? I mean, I was. That is why, because as you told that when the boundary conditions are unique, when we solve it by Uniqueness theorem, the potential will be same for both the system. That part I understood. That is quite understood. But there was, I think it is electrostatic energy, sir. Half of E square. That part I get. I think so. E square, E plus that electrostatic energy. That's what I'm basing it to be half. I will check.
Yeah, you can check.
Sir, and one more thing is when you calculated this thing and finally in place of m you put me by 2 when you did that for that.
Yeah, because if I have an electron here, the image charge also will be an electron. So mass will be same.
So what I'm asking is why did you put me by 2? That is what my question is.
If the mass
In
is
energy.
if the mass is same, reduced mass will be me by 2, no?
Okay, you put, okay, you use this mu is equal to me by me plus me. There you have substituted me there and you have put me.
Yeah.
Okay, sir. Sir, and I was struck in solving an integral, sir. This is a homework. Finally, you told that find the normalization constant. C squared is equal to integral 0 to pi sine theta d theta, 0 to 2 pi d pi sine power 2l d theta. There, I'm finally getting the 2 pi c square into integral 0 to pi sine 2 power l plus 1 into theta. How to do that integral, sir?
Sine power 2l plus 1 into theta.
Yeah, that in integral 0 to pi sine power 2l plus 1 theta.
I think you just write sine theta as e power I theta plus e to the minus I theta, and then maybe you should integrate it in a complex plane from 0 to 2 pi. That is what you do, no, in complex integrals. Whenever
Yes.
of sine theta.
Yeah.
Okay, then we will close.
Thank you.